Hi. So also bringing something kind of new to the crowd, my talk should not probably called investigating muon content in extensive air shower using Pythia 8 because I will not be showing actual shower observables. It's still at the ongoing effort stage and not as I have results for you to see today. But I'm also maybe renaming it as bringing Pythia 8 for cosmic ray air shower studies into the race, in addition to the other models we've been discussing so far this week. So also, it is one of the hints that would perhaps help solving these muon puzzles that we've discussed before. But to jump directly into it, PCI8 is a more general purpose models, which is well tailored for LHC experiments. So they have good descriptions of electron position, proton-proton, anti-proton collisions, and also using now their extensions for the nuclear interactions, proton-lead and lead-lead collisions. But it has an incomplete data descriptions because there's these problems with the stringent enhancements. There's the reach effect at the highest multiplicity that you see from the proton-proton collisions. There's also some incompleteness when it comes to the baryons productions in charm and bottom productions and the forward particle spectrum. And these are also linked to limitations for air shower applications where they look at only very high energy interactions. They're initialized for fixed targets and beam, and on this simple version of Pythia, there's no variation allowed. And there's only a limited amount of beams that are allowed. So this motivates a need for this nuclear interaction extension. You have two options available. Since the version 8.307, you have this Pythia cascade wrapper class, which Peter described in his talk on Monday, where you have a simplified model to what Engentier would be, which would be the second option, where you have fixed targets, hadron nuclear interactions, and also decays up to the with a momentum energy of the incoming hadron down to 0.2 GeV. But it is a very simplified description. And the second option that you would have is using this Engentier model, where the nuclear geometry is given by this global model, and you stack the individual nucleon collision on top of each other, and then you hadronize them all together. And in the latest update of the models, the Engentier model has been updated, and this now allows the variation of the incoming beam and the energy on an event-by-event basis, which is a really strong feature. And using this, I've been recently tabulating cross-sections using the latest version of Pythia, and I want to show you some of these results. So cross-sections have been tabulated not only for total and inelastic cross-sections, but also for all these sub-diffractive processes that Pythia offers us, which have single diffraction, central diffraction, double diffraction, and all of this. So I adapt my work on top of what Maximilian Renninghaus has been presenting in the past. And so these are basically the same points that he had. And in addition to this, I add a Pythia green line here for the latest version. And I also took the liberty to add the Auger points that we have here from the for the proton-proton inelastic cross-section on the left. And you can see for the pion proton on the right. So for proton, good agreement with the other models. And for pion proton, slightly below the more than Sibyl or EPOS we see here, which is still in following the same shape as this previous version that we were working with. Now moving on to proton oxygen and pion oxygen cross sections. Here, Pythia still finds himself to be on top of all the more cosmic ray models we use, but we can see an improvement as from the previous version where it has lowered by a certain gap. Now you might be finding this strange feature here when you look at the pion oxygen. This is a current technical problem within the code, within the Engentier model, and it's being worked on. I do not know as of now if we would have a more smooth line that would resemble the previous version, or if this Pythia line would therefore merge better with perhaps maybe the Sybil 2.3 line. This is up to see, but it's still the results that I wanted to display today. Now, this is proton oxygen, but this cross-section here is proton air that we're looking at. So I wanted to add as well this proton nitrogen curves that you see in dashed, and as expected, the cross-section is rather low, but still not within the uncertainty bar of what would be this proton air cross-section motion. Continuously, and this is a very busy plot, I have plotted four different projectiles against a target of nitrogen for the latest models that we have. So the solid line that you see, which is above on every single types, would be the Pythia line from the latest version using the Ganton model. And then you will find the QGSjet line to be the dotted one that you can see usually on its own, except for the proton nitrogen here, where all the models seems to be superposing with one another and matching to the proton air cross-section. And then we have the Sybil lines here, and then EPOS LHC and EPOS LHCr, where EPOS LHC is a tad higher than the EPOS LHCr cross-section, as Tanguy just displayed in the previous talk for proton air. But this is a rather interesting result where you can see that the behavior of Pythia is exceeding every time. So question being, is this incorrect? Is this simplified model? Can we use this to gather more muons in the future? This extension. And so then, after using Pythia standalone as is, we want to interface it with Corsica 8. So the previous interface to Corsica 8 was done using this Pythia cascade class, where the tracking of the interaction was done with Corsica 8, and then we would call every time we would need to provide a hadronic nuclear constructions, perform these collisions, or perform a hadronic decay. But now in the new version, the efforts are that we still want to have the tracking done by Corsica, and we want to call Pythia or Engantia depending on the type of collisions we are studying. So for proton-proton, we would call the standard Pythia model, and whenever we would have a nuclear included in the interaction, we would call them Engantia. We would be able to have a single Pythia instance and varying the energy and the beam on an event-by-event basis, which is really strong for computational reasons and allows us to have more liberty and faster simulations. In that note, we would interpolate the cross-sections from the earlier computed table, since getting this cross-section is rather slow. But another additional things that needs to be done at the moment is that we need to make this similar superposition model, because the remnants that we get whenever we collide nucleus together are not, we do not have the cross-section stable for them, and we do not know what to do and how to deal with them, and we still want to propagate them and include them in the whole shower development. So we would need to introduce them similar as what's done for Sybil, the semi-superposition model. And in order to have faster simulations, we want to use this system that is a new feature in Pythia, to have this reuse file when they make fits and PDFs for all types of collision within the whole energy range that we want to be using. So for us, it would be all the projectiles and targets that we have, ranging from the hadrons to the highest nucleus that we would have as projectile or targets, and then the whole energy range from 100 GeV to 10 to the 2021 EV to have the whole picture. Now I want to talk to you about how it's good that we have Pythia implemented in Corsica. Maybe we will have some showers, but do we expect them to be good physics? Do we explain them to be correct? And so, as previously discussed by Peter Scans or Pythia 8 can be tuned. There's already the Monash tunes, Atlas tunes, and then more recently a forward physics tunes. And there's now an ongoing effort here in Wuppertal to make yet another tune, which at the moment would be using SPS and Fermilab fixed target data. And we would want to tune beam remnants parameters, as well as perhaps play with color reconnections parameters. And how that would be done is that we would go and fix the parameters step by step. So first look at proton-proton collisions, then look at pion-proton collision, then look at pion nucleus, and so trying to gather this nucleus that are carbon, nitrogen, oxygen. So here would be most likely the Na61 data sets, and then proton, again, carbon, so perhaps again the Na61 data sets. And this would all be, these ones at the moment I have, we would look at the hadron production from Na49, and also the hadron production here at these different energy scales. But one problem that we would face with Pythia is that whenever you go at such low momentum, then we would not be able to run them with Pythia. Therefore, we might have to focus only on the highest energy, since you do not want to run Pythia at less than center of mass energy 10 GeV minimum. Already at 15, it's already aborting many events. So this is one of the constraints we have when working with Pythia. Other data sets that would be of interest would be self-scatterings from Na8s, or Fermilab experiments. Here we would have total cross-sections in pion-proton, kaon-proton, proton-proton, and anti-proton-proton for a range of energy, which again, the first publication here would probably only be on the upper half, so starting maybe 100, 150 GeV to there, and then this is just the continuation of the measurement campaign they had. Yeah, so this is a lot of measurements, and these are all interested to be included in the etude, but furthermore, we could perhaps look at Na22 or even more measurements in the future as well. And so to do this, I use this Rivet framework, which is good for analysis and also to preserve datasets, and it's part of this whole idea of having heavy data and preserving everything and online, and any user can come through and run their analysis. And so here I want to look at this Na61 shine data, which is the one that one of the ones that Ralph highlighted just earlier. And you see here for a negative pion to a carbon target, we look at the outgoing positive pion for this first energy, which is 158. And the data sets are here shown in black. And then you see all the LHC tuned model, which are shown by the different colors. So we would have QGHZ here closer to datasets in the early momentum, but then diverging in the higher state in the higher momentum, and then you would have all the other models following a more excess trend, and then less here. But of interest to see is that these are LHC tuned. Now, if I put the older version of the models, which were then SPS tuned, you can see that the description is much better of the Na61 dataset, since it's an SPS energy model dataset. And therefore, that's why I would like to focus on this SPS datasets to include the tune of the Pythia, and therefore give a better description in this area, because Pythia is mainly tuned at LHC energies as well. Therefore, does not at first sight here have a good description of the dataset in green. So after all of this, you would have, therefore, your implementations of Corsica 8 and Pythia 8, so you would be at showers. And then another step would be to implement Pythia 8 within Chromo, which would help us to get tables for MCEQ, and then we would be able to gather some lepton boxes from there. And all of this would give us more information of how the showers behave. And if you would have your Pythia standalone curves, and then your you would have your tuned curves, and there's a lot of things to learn here. As a last outlook, I would like to talk about the idea of a global tune for air showers, which would come after the idea of this more to close the loop of the general tuning idea, where we use only accelerated datasets. In here, we would want to use both shower observables and accelerated datasets. Shower observables, which could be linked to the muonic shower properties, or the electromagnetic shower properties, or even the cross-section inferred from the X-max distribution tails, or the mass compositions of cosmic ray. And all of this was discussed at the workshop that we had on the tuning of hadronic interaction models back in January in Wuppertal. Well, many of us here in the crowd were part, and I think these are good efforts, and we should highlight them. And I think that would be the end of my talk.
Thank you for your talk. And now questions. Rajin.
Now, if you at the beginning, what you showed about the cross sections for nuclei, I think the differences are too big because the cross sections are mainly given by geometry of the nucleus. And we do have a very good understanding, at least for the intermediate nuclei and for the very heavy ones. And so we will have to look at the different codes because it looks too strange that the differences are so big as you have them in the plot. And it could be that we really compare different things. Like years ago, we had a situation that some models had a quasi-elastic cross-section included and others not. So one really has to be careful what is shown here and what is used. And it has nothing to do with your work, but what you show actually is the difference is too big. At least, for example, helium looks really very strange to me.
So as a quick disclaimer,
yeah, so it's
all the curves except for the except for the Pythia curve, I got them during this very conference.
Okay, good. So maybe
So it is possible that maybe there was some fast tracking, but originally I intended to show this plot singularly with the Pythia and the Auger photon air.
I only wanted to raise a concern there because it.
But I do understand.
Yeah. Okay.
More questions? No online. Actually, I have some more comment. If you come back to your cross sections, well, proton carbon, pion carbon, they have been measured by a couple of experiments, notably Carol Roberts and recently NA61. You can check NA61 paper there, you will find all the references. And inelastic proton carbon, pion carbon. And I would repeat what comment I made to Peter's comments. There is no viable alternative to Glauber approach. Just, it doesn't really make sense to try anything. It's simply like when you use this inelastic rate, it's irrelevant. It's dominated by central collision, small bits. Cross sections, as Ralph said, this is size. This is the Glauber approach, the periphery.
But the work that Peter displayed is the one in olive, like the yellowish curve. The one in green, he is not using this simplified model, it's using the Engantine model.
But you see, it's still something like 20%. Cross sections for showers is the very, very important, the most important thing. It's the first interaction point. This should be most reliably done. So I really urge you to switch to Glauber approach. If no more questions, we thank